Yeah, thank you, Chuck, for the intro, and good evening to the Longmont Amateur Radio Club. I'm Carl, K9LA. In Fort Wayne, Indiana, that's up in the northeastern corner of the state. We're pretty far west, but we're still in the Eastern time zone. If we drive about an hour west, we'll be in Central time. So there's good things and bad things about that. And we still change our clocks like most of the states. Let me bring up my screen here. There it is. Okay, it's on my screen, and let me just make it full screen. Okay, it just showed up full. Well, no, it didn't. It went away. Okay, there we go. Good enough. So everybody can see that?
Looking good, Carl.
Okay, good. So what the title is what makes ionospheric propagation? And we're going to run through a variety of topics. There's my email, k9la@arrl.net. I have a website, a lot of propagation stuff on it. And Chuck, I plan to send a PDF of this presentation to you either tonight after I'm done or tomorrow morning.
Thanks,
so
sir.
If anyone wants to peruse it and wants to ask questions, well, there's my email. Glad to answer any questions. So who is K9LA? Well, I won't get too deep into this, but I've been around a while. Got my novice in October 61. Out of Purdue, design engineer for Motorola and then Magnavox Raytheon. And I enjoy several aspects of ham radio. And my wife is Vicky AE9YL. She was first licensed when we lived in the Dallas-Fort Worth area. So that's enough about me. Oops, how come that thing didn't minimize? There it goes. So what we'll talk about is our atmosphere, the sun, the ionosphere, HF propagation, solar cycle, space weather, and cycle 25. That's a lot, but like I said, you'll have a PDF to peruse if you're interested in going over this again. So let's look at our atmosphere first. There are four major constituents in the atmosphere. Molecular nitrogen, which is N2, atomic oxygen, which is O, molecular oxygen, which is O2, and nitric oxide, NO. And when you throw all that stuff in the atmosphere, about 78% is nitrogen, 21% is oxygen. Then there's about 1% other gases. Now, each concentration varies with altitude, and also the concentrations vary over a year's time frame. So there's a lot of things going on up above us. And that leads us into the sun, which of course is my favorite star. And here's some very basic facts. There's on the left is an image of the sun compared to the size of the planets. You can see the sun kind of really swamps Jupiter and Saturn, and all the other ones are even smaller. If you look hard enough, you can see Mercury and Venus in there too. The two blue ones are yeah, right. Okay. Uranus and what's the other one? Neptune. That's right. Yeah. Okay. And the sun is a perfect sphere. It's a plasma, which is an ionized gas. That means there are free electrons running around in there. It creates heat by nuclear fusion, which turns hydrogen into helium. The sun's about 4.6 billion years old, and it's in the most stable phase of its life right now. It's going to burn out in about 5 billion years. So the gentleman who had half his lawn grass, half his lawn mud. I think you got some time to fix that. So you should be okay here. So the sun radiates electromagnetic radiation at many wavelengths, and that's what that sketch on the left shows. It radiates very short wavelengths, which are gamma rays and X-rays, to very long wavelengths, which are radio waves. And that chart shows where those different wavelengths are. Way on the left, to the left of ultraviolet, is the gamma rays and X-rays. And you can see you get into TV waves, microwave, shortwave radio, and that's the longer wavelengths. Most of the most intense radiation from the sun is at visible light wavelengths, which is about 400 to 700 nanometers. And of course, that's why our eyes adapted to the sun, I guess. Now, the energy of a photon, that's the particle representing a quantum of electromagnetic radiation. Energy of a photon is inversely proportional to its wavelength. So the shortest wavelengths have the highest energy. So gamma rays, X-rays have lots of energy, and so does ultraviolet. The most important range of radiation for our amateur radio activities is those very short wavelengths. And if you follow that green line at the bottom, down to the left, and then back up, you can see where the ionizing wavelengths are. Those are the wavelengths that make the ionosphere. Very short. One thing you ought to note is look where 10.7 centimeter solar flux is. That's about 1 million times less energetic than extreme ultraviolet. So 10.7 centimeter solar flux has nothing to do with ionization, but it's one of a couple proxies for the ionizing wavelengths. The other one being sunspots, and also there's some other wavelengths that we could use to as a proxy for those ionizing wavelengths. So in the ionosphere, and there's a little picture of how do you tell if a band is open? Well, if you get hit in the head with some RF from a station far away, that'll tell you the band's open. Don't believe that, though, of course. So all that radiation creates regions of ionization in the atmosphere. And it depends on the wavelength of the radiation and the altitude and concentration of all those atmospheric constituents that I talked about earlier. There's a summary there, the last 3 bullets of which atmospheric constituents contribute to the various regions of the ionosphere. And that sketch on the right shows that during the day, there's a D region. There's an E region, there's an F1 and F2 region, but then at night, it basically comes down to a weak E region and the F region. And that's what's most important are the free electrons. Those are electrons that are stripped from a neutral atmospheric constituent in the ionization process. And that's what gives us propagation. So here's some general characteristics of those regions. The F region is roughly 150 to 400 kilometers high. F1 region is only during the day. F2 is all day. And at night, as we saw in that previous slide, that the F2 region is still there. It's kind of reduced, but it's still there to give us nighttime propagation. It's the highest in altitude, and that gives us the longest hops, which means, hey, that's how you most of the time you work DX, which with long hops. And also the F region has the highest electron densities, and that's best for the higher bands, 15, 12, and 10 meters. E region's roughly 90 to 150. That's also where sporadic E occurs. Because it's lower in altitude, it gives shorter hops. It can actually block signals from getting to the F region if the E region is of a high enough density. At night, like I said, it pretty much goes away. It's kind of weak, but it still can affect 160 meters and much longer wavelengths, 630 and also 2200 meters, which are new bands for us. The D region is 60 to 90 kilometers. Its claim to fame is it's a detriment to propagation because of absorption. That's ionospheric absorption. At night, it's pretty much out of the picture, but there is still some absorption on the low bands from the lower E region. So we don't ever get rid of absorption. And on that sketch on the right, you can see there's day, night. Also at solar minimum, which is the R equals 0 curves, and R equals 200 is a typical solar maximum. And you can see that what the difference in the ionosphere is versus day and night, and also over a solar cycle. How do we measure the ionosphere? Well, we use ionosondes, and what they are just radars looking straight up. They send pulses when they sweep from about 2 megahertz up to 20 megahertz. And what they do is measure the time of flight. In other words, how long does it take that pulse to go up and come back down? And also what you can tell from that is how dense the E region and the F2 region is, and sometimes the F1 region when it's there. Now, our propagation generally isn't using angles straight up, although NVIS, near vertical incident propagation, is at very high angles. But as you consider lower elevation angles, they can be refracted at a much higher frequency. So all of that translates into the development of a worldwide model of the ionosphere, which is used in our propagation predictions. So HF propagation, what does it take to make a QSO? Well, there must be enough ionization to refract and bend the signal back to Earth. Otherwise, it'll go through the ionosphere, never to be heard from again. The amount of refraction that a wave incurs is inversely proportional to the square of the frequency. What that means is the higher frequencies don't refract as much, therefore they need more ionization. And in addition to that, there must be, the loss must be low enough to hear or detect the signal. Now we can control some of the loss parameters, for example, transmit power, antenna gains, receiver sensitivity, man-made and atmospheric noise. We can resolve the man-made noise by fixing problems and or using directional antennas. Now, some of the things we can't take care of in the loss environment, and that's absorption in the D region. Also free space path loss. The wave spreads as it goes through space. And of course, ground reflections, we don't have any control unless you're sitting right on the coast and you're talking to a far distant station on some coast somewhere else. And if it's all water in between, that's good. Okay, distance versus elevation angle. If you have too high of a ray, look at number 1 there, you can see it gets bent a little bit by the ionosphere, but it goes through. So what that says is there's not enough ionization for the frequency that you're on. In other words, the maximum usable frequency isn't high enough. Now look at ray 2. That's the first one that comes back to Earth. And that's because there's enough ionization to refract it back to Earth. And where that number 2 hits, Well, you're not going to hear anything closer in. That's the skip distance. Now, ground wave can cover some of that. And if you go lower in frequency, a near vertical incident skywave can cover out to the skip distance. But generally, you'll have a skip distance, which is could be quite long. And of course, as you go lower elevation angles, they go farther out, like 3 is farther than 2, 4 is farther than 3. And as the elevation angle gets lower, it encounters the ionosphere at more of a grazing angle, and that causes the MUF to go up. And there's a little table there kind of showing some typical numbers. For example, if in the conditions on the previous slide, if you send a 50-degree signal, a 50-degree elevation angle wave, it'll go about 474 kilometers, and the highest frequency that will refract at that elevation angle is 10 megahertz. Now, if you can put energy down at 5 degrees, it'll go about 2,900 kilometers. And the highest frequency would be 25.4 megahertz. So you can see the advantage of having lower elevation angles. It gives higher MUFs and farther distances. So modes. There are many modes in HF propagation. There's multi-hop, which is shown on the right there. It just goes up to the ionosphere, comes back down, reflects back up to the ionosphere, comes back down. It can do that for several hops. The E region or the F region can do that. There's sporadic E propagation, transequatorial, which is to South America on 10 and 6 meters if you're in the southern states and in the Caribbean. Short path, there's long path. You have to remember the two ways to get to the shortest distance between 2 points on a globe is a great circle path. There's one that goes the short distance, and there's the other one going around the longer distance, short path and long path. Multi-hop is likely the most prevalent mode on HF. And just a comment about sporadic E, it's great for 6 and 10 meters. Not highly dependent on a solar cycle, so it's pretty much there every year. And we're coming up on the summer sporadic E season, and it's best during the summer months in late morning and early evening, June, July, and August. So keep your radios, listening on 6 meters and even 10 meters, and you'll maybe be surprised by some good openings because of sporadic E. Solar cycles. Okay, they determine which bands are open, and there's a picture of the sun when it has lots of sunspots at solar max. Then there's a picture there on the right, solar min, where there are few or no sunspots. We are now in the rise of cycle 25. In 2017, 18, 19, pretty much was solar minimum, and the sun looked like a lot like what that picture is on the right. We had lots of 0 sunspot days. So what's a solar cycle? Well, it's also known as a sunspot cycle. Take a look at that sketch on the right. It's the time period from a very low number of sunspots, which is A, through a maximum number of sunspots, which is solar maximum, and that's B on that curve, and then back down to a very low number of sunspots, which is C. So a solar cycle is A to B to C. Approximately 11 years. That's an average. Some are shorter, some are longer. And on average, the rise time to a solar maximum is about 4 years, and the descent time is about 7 years. So you can see where solar minimum is on that sketch, A and C, and solar maximum is up at the B part. So why are solar cycles important for us? Well, they are certainly important for the higher bands, 15, 12, 10, and even 6 meters. The area around sunspots emits extreme ultraviolet radiation to ionize the F2 region. And let me reiterate that the F2 region is the most important for long distance contacts on HF. When we have more sunspots, there's more extreme ultraviolet, which is the true ionizing radiation of the F2 region. So we have more ionization. That means the higher the maximum usable frequency that you can use, and it gives us the best propagation on the higher bands. And of course, that's around solar maximum as indicated in the annotation above the cycle sketch there. Important for the low bands, 160, 80, 60, 40. When we have less sunspots, we have less ionospheric absorption, less loss from the D region, and less disturbances to propagation. That's the best for the propagation on the low bands. Doesn't say you can't work the low bands at solar maximum, but it's more fun to be on 10 meters with S9 plus signals at solar max than being on 160 meters with signals at the noise at solar max. But if you're a dedicated low bander, you can be there throughout an entire solar cycle. In general, 30, 20, 17 are good throughout a solar cycle. You can see where the best propagation for the low bands is. There's around the A and the C on that sketch. So when are the bands open? Well, the lower bands are best at night, although you can talk pretty far on the low bands. In fact, I'm about 1,000 kilometers to the East Coast, and I can have a QSO on CW with an East Coast station on 160 around local noon. I got to run maximum legal power, have a good transmit antenna, good low noise receive antenna, but it's possible. Normally, though, the lower bands are just for local type during the day, and they have much better propagation at night. Those middle bands, 30, 20, 17, are generally okay day and night. The higher bands are best during the day when the MUF is highest. When we're at solar maximum, they'll even stay open for several hours during the evening. And if you ever have a solar cycle like cycle 19, which was peaked in 1957, late 57, 10 meters could be open almost round the clock. That was the highest solar cycle in recorded history. And if you were there for that, you had a lot of fun. 6 meter propagation via the F2 region is best at solar max in fall and winter. So we're going to have to wait till this coming fall and winter to probably see a much better chance of 6 meter propagation via the F2 region. But don't forget sporadic E in the summer. We'll probably have lots of that. The higher bands, 15, 12, and 10, follow the sun. In other words, the propagation is generally northeast through southeast in the morning, southeast through southwest in the afternoon, and southwest through northwest in the evening. Kind of a general rule. So if you have a directional antenna, just have it follow the sun during the day and you'll have lots of good results. And of course, the digital modes have an advantage over sideband and CW. In fact, the last solar minimum, it'll go down in history as the most active on the higher bands due to the digital modes. If we didn't have the digital modes, all you'd hear most of the time is noise. But those digital modes can detect signals farther down into the noise, and that was quite kept a lot of people interested in the higher bands, even though we didn't have many sunspots at all. Space weather. Okay. Just a caveat, what we're trying to do is simplify some very complicated atmospheric and ionospheric processes into simple statements about HF propagation. Sometimes that can work, sometimes it can't. We have trouble with predicting the day-to-day variability of the ionosphere. In other words, what's the ionosphere look like today? What's it going to look like for tomorrow? We struggle to predict that. And we even have a lot more problem with short-term events, solar flares, geomagnetic storms. We just don't understand things enough to really have short-term predictions. The two parameters that I think are important are SFI, which is the solar flux index. Remember, I mentioned that it's a good proxy for extreme ultraviolet. It can indicate which of the higher bands may be open. That could be impacted by the K index. We'll get into that a little bit. And there's a general correlation between the solar flux, sunspot number, EUV, and also that term at the bottom on that banner, MUF, US Boulder. That comes from QRZ.com, N0NBH banner. It's at other places, but it gives a pretty good indication of what's going on. Solar, like I said, the solar flux can indicate which of the higher bands may be open. The K index tells us how disturbed the Earth's magnetic field is, which could mean the F2 region may be screwed up. And there's a general correlation between Ka, B sub Z, and SW. When I say general correlation, for example, if the solar flux is high, generally the sunspot number is high, the EUV, extreme ultraviolet radiation, is high, and the MUF US Boulder is high. Similarly for the K index, if the K index is high, the A index probably was high. BZ is large negative, and the solar wind speed is very high. So let's take a little bit deeper look at those two parameters. The 10.7 centimeter solar flux, from a solar min to a solar max, it can vary from 65 all the way up to 350. The daily data is very spiky. If you take the daily data and average it over a month, the monthly means, they're still spiky, and that's why we do even further averaging to give us smooth values. Now, for 15 meters, we desire that the solar flux be greater than 85 for a long time, not just several days, but for a long time. For 10 meters, we desire it to be greater than 100. Right now, the smooth solar flux is about 140, and you can see why 10 and 15 have been open last fall and winter. We're going into the summer where the MUFs are lower, but they'll be back up this coming fall and winter. And cycle 25 will be a little bit higher, so that's going to make things even better. The 3-hour K index, it's a logarithmic ratio from 0 to 9. 0 is quiet, 9 says the Earth's magnetic field is disturbed, which, like I said, that could mean the F2 region is screwed up, which means the higher bands aren't very good. Generally, we desire the K index to be less than or equal to 3, unless you're a VHF enthusiast, in which case you want a high K index for aurora propagation. The daily A index, it's a linear from 0 to 400. It's an average of the 8 3-hour K indices. And 0 is quiet, 400 says the Earth's magnetic field is disturbed. So if you look at that N0NBH banner on whatever day and compare it to the numbers here, you'll have a good idea of, a decent idea if the bands are open or if the bands should be open, but they're not because the Earth's magnetic field is screwed up. Now, you don't have to worry about all that stuff. The easiest thing to do is just go look at some real-time QSO data. This is dxmaps.com. You can select a view. I selected a world view. You can select a band. I selected 10 meters. This was from February 27th of this year. And that's from So the 11, that would be a 1044 to 1053 year time out there in Colorado. And you can see 10 meters was doing pretty good. They were passed to South America, to Europe. There's similar info at PSK Reporter, WhisperNet, the Reverse Beacon Network. There's a URL to go look at that. And also the Northern California DX Foundation has beacons on 2017, 15, 12, and 10 meters. And those beacons in a 3-minute period, you can tell what worldwide propagation is on a given band. And there's some software from VE3NEA that helps you sync your computer up to the transmit times of all 18 beacons. So it'll give you a good picture of what's going on. Okay, cycle 25. If you've only been licensed for several years, you may have been asking what's so great about 15, 12, and 10. Because most of the time there was only noise and not many signals. These bands are better now because cycle 25 has risen high enough. And you'll be amazed what these bands can do with moderate power and simple antennas. Here's a plot of the rise of cycle 25. That's the thick red curve. We have, let's see, what does it say? 35 months of data from solar minimum, which was in December 2019. And I've also plotted 3 other solar cycles on there. Green is the cycle 24. That was a very small cycle. It was the smallest in our lifetimes and the 4th smallest in recorded history. Orange was an average cycle. If you take an average of the maximum of all 24 cycles, it comes out pretty close to what cycle 23 did. And the blue is a moderately big cycle, cycle 21, which peaked in 1979. And you can see right now, cycle 24 is tracking the small cycle 24. I believe we still have time for it to get to an average cycle, which means the higher bands will be better, more chance for 6 meters, but we'll just have to wait and see what happens. I should mention there have been, I'm aware of about 55 predictions for cycle 25. Why so many? Because we just don't fully understand the solar cycle process. So there are predictions from a very low cycle to a very high cycle. And predictions are good, but actual data really trumps all that, all those predictions. And right now it sure looks like we're not going to have a really big cycle, but that's okay because it's big enough to give us 12 or 15, 12, and 10 meter propagation. Here's some websites with space weather data. I mentioned that N0NBH banner. There's several others. You might be familiar with Dr. Tamitha Skov, WX6 Space Weather Woman. She gives videos of what the sun's doing and how it affects propagation. So that's good to listen to or watch, I guess. And there's a lot of other websites that have much more detailed data. So summary, get on the air and operate. Experience is a great way to know, to knowledge. Make QSOs and contests, go after worked all states, go after DX Century Club, go after CQ's worked all zones. Especially have fun this fall and winter on 15, 12, and 10, because cycle 25 is still going up, maybe not as fast as we'd like, but it's still going up and it ought to give us some great propagation on those bands this fall and winter. And use the digital emoji if you're power challenged or antenna challenged. There's some propagation references, ARRL handbook and ARRL antenna book. There's also a new ARRL propagation book coming out. It's at the printer, as I understand it. Bob Brown, NM7M, who's a silent key, wrote the Little Pistol's Guide to HF Propagation. That's a good, easy read. It's out of print, but it's available on my website. It's a 15 megabyte download, which that shouldn't be too much of a problem nowadays. And of course, there's the CQ Shortwave Propagation Handbook, 4th edition, which is a 2021 revision of the old 1995 version. So, oops, that's all I had. We got out of that. So if there are any questions, oops, there we are. Be happy to answer them.
All right. Thank you very much, Carl. Appreciate it. Anybody any questions for Carl?
I just wanted to say that is the clearest explanation I've ever heard of the whole subject matter, but in particular, what the index has made, and I really appreciate it.
Well, thank you. You're welcome. There's a lot of stuff out there, and yeah, it can be overwhelming.
It definitely was explained a lot better than I remember in classes. So, yes, thank you for that.
So I have a question.
Yes.
So I'm trying to fill in. I have 3 more states I'm working for on 80 meters. So I was up early one morning and 80-meter propagation was just horrible.
Yep.
And so I went and looked at the probability maps and they all said they were good. And but I then went to N0 Herman's site. And the only thing I could figure out was the only thing that was off, the flux was high enough, everything was good, except the solar wind was up above 500 kilometers per second. It was like 550 or so. So what's the physics behind that affecting HF?
Well, what happens is when the sun's magnetic field, which is also known as the interplanetary magnetic field, couples into the Earth's magnetic field, that can screw up the F2 region. And that's what's going to kill a lot of propagation. There can be more absorption. The MUFs could be down. But a key indicator is when the solar wind is much greater than about 400 kilometers per second. And the K index is generally greater than 3. That's what you should look out for. And that B sub Z component, that's the component of the interplanetary magnetic field that is perpendicular to the ecliptic. So what's the ecliptic? Well, that's the plane in which the Earth goes around the sun. Now think of something that's perpendicular to that ecliptic. That's also the way the Earth's magnetic field is, pretty much perpendicular to the ecliptic.
Yeah.
So when that B sub C goes highly negative, that means all that solar wind stuff is going to get into the Earth's magnetic field and screw up the ionosphere. It's like I said, we don't understand short-term events much. We have a general idea, but I can't give you an exact answer of, well, that's because, the solar wind was this high, the K index was this high. But in general, we don't want a high solar wind speed, and we don't want a high K index either.
Yeah, okay. I didn't expect an exact answer. What confused me a little bit also was Paul on his website said the higher the speed, the greater the pressure is exerted on the ionosphere, and that just kind of threw me.
Well, on the Earth's magnetic field.
Yeah. Right. Okay.
Yeah. All right. Which then, because the ionosphere is charged particles, it has a lot to do with the Earth's magnetic field.
Yeah. Okay. All right. Well, thank you.
You're welcome.
We have a question in the room.
Mm-hmm.
Go ahead, John.
Oh, on the picture you showed of sunspots, was that like visual, probably not visual light, or what spectrum of light was that in? And also that leads into, does it matter where on the sun the sunspots are or not?
Hold on. I think I know what that picture?
Yeah, this picture.
Yeah. Well, that's more than likely, I think that's just visible light. And the sunspots show up because they are cooler than everything else around it on the sun, and that's why they look dark. Where they are, it doesn't matter that much, but where they are kind of tells us where we are in a solar cycle. When a new solar cycle starts, the sunspots are at the higher solar latitudes. And as a sunspot cycle progresses, the sunspots form closer and closer to the solar equator. That's one of the ways we can tell which cycle a sunspot is from, because solar cycles do overlap. And from what I've seen, there's an overlap of about a year when there are sunspots from the old cycle and sunspots from the new cycle. And that's one way to tell is the solar latitude. We can also measure the polarity of the sunspot. It's just a magnetic field coming out of the sun going back in. So there's a polarity to it. And that's the other thing that pretty much pins down that these sunspots are from this solar cycle.
So would it matter if the sunspot is if it's on the opposite side of the sun such that we can't see it?
Right, because the solar, we can't see them, but of course the radiation from the sun at the extreme ultraviolet wavelengths is not going towards Earth. So the only ones that matter for propagation, of course, are the ones that we can see on the solar disk. That says that they're facing Earth, or we're facing the sun.
But the Earth is rotating, so would there be a point where would there be a time where sunspots don't matter if that were true?
In a way, yeah, night and day. The F2 region goes away, right? Okay. And the E region.
I got you.
Yeah. Yep.
And Carl, there's a question in the chat about what's the theory of the 11-year cycle?
The theory is why 11-year cycle? No, we don't understand that. One of the interesting ones is the alignment of Venus, Earth, and Jupiter. There's a word for it. Any astronomers in the group here? Is it syzygy or scissor? Some funny word that's spelled with Z's and Y's and all that. But when those three planets line up, that's about an 11-year cycle. So could it be that when those three planets line up, there's a tug on a tidal force in the sun, since it's a fluid, that causes it to kind of sync up with what Earth, Venus, and Jupiter are doing every 11 years. Other than that, I'm not sure we have a good idea what's going on.
Thank you.
Mm-hmm.
I have one question. You talked about the angle of radiation or propagation from your antenna. How do you determine that? And what can we do to affect that?
Mostly with antenna modeling. You can put your antenna at various heights and see how the vertical pattern is. You can't do too much about that, really. Well, you can put up a taller tower. That's why these big contest stations like K3LR, W3LPL, they have 200-foot towers and multi-element Yagis, and they are very concerned about putting lots of energy at low elevation angles. But an antenna at 30 to 40 feet on 15, 12, and 10 will give you lots of fun. You won't, if there's a pileup and you try and get in, you won't be the first one, but more than likely, eventually you'll work them. So the only thing we can do is move the antenna up and down. And people have, I think, done that with a like a hazer system or a telescoping tower, but I don't think it's really worth all the effort to go through to do that.
Okay,
In
thank you.
general, you want your antenna as high as you can get it. And that also gets it away from maybe some ground clutter around your house, et cetera, too.
All right. Thank you.
Mhm.
Yeah, and Ted put up the word in the chat, a little definition, the SYZ.
Yeah, there you go. Yes,
Yeah.
I don't even know how to pronounce that. Well,
So,
syzygy or something. I don't know, whatever.
I want to see the chat here. Sorry.
Yeah, those three planets, Venus, Earth, and Jupiter, do give the sun the highest force. You know, Venus because it's so close, and Earth it's kind of close. Jupiter it's far away, but it's so big, and that's what does it.
And I have found if you watch the Space Weather Woman on her YouTube channel, goes into great detail on some of the stuff, especially with like CMEs, coronal mass ejections,
Right.
and how they can, if we're going, if it's the sun's starting its turn and we're not quite there yet, it could miss the Earth or bypasses on the left or the right and things like that. It's pretty cool to watch some of that stuff and how she explains it. It's really neat and educational.
Yep. Yeah. There's orbital resonance and the solar cycles. A link to that's probably very interesting to read.
I know we had let's see, there was for CME a couple of weeks ago. I think it blacked out some of the polar region for amateur radio. So,
that's a whole nother subject, disturbances to propagation. So,
yeah, it is a whole other subject.
Yeah.
So, all right. Anybody else got any other questions, comments? Anybody? Anybody on the call? Zoom call? Well, Carl, I want to thank you very much. That was super interesting. Definitely got into more detail about propagation and solar cycle and explained it a lot better. I think I'm going to let our instructors read that because they can start using it in their training class and make it a little bit more understandable. Because that's something that always kind of confused the heck out of me.
Yeah. Well, there's a whole nother presentation about NVIS, which you mentioned, MCOM stuff.
Yep.
And if you'd ever like me to do something like that, I'm available. So.
I definitely will be contacting you. I have another club I'd like you to present to as well. So.
Oh, okay.
You'll be hearing from me. And it's a DX club, so it'll definitely interest. And that's all they do is DXing. So this is something right up their alley there.
So Longmont is kind of north of Boulder.
We're just a little bit east of Boulder.
Oh, east of Boulder.
Or northeast.
So not too far from Wyoming then.
Nope, not that far from Wyoming.
Yeah.
But Pat W1PGE, he's our club secretary, moved to Wyoming and loves it up there. So.
Oh yeah. Back in my younger days, I was a airplane and instrument flight instructor, and I owned a Cessna 170. And one of my longest flights was from Cheyenne to Billings.
Okay.
That was we were watching the gas gauges. That was about a 4-hour flight in the 170, and the 170 had about 4 hours 20-minute gas tanks.
And hoping for a tailwind.
Yeah, there you go. Of course, if we ran out of gas, there'd be lots of places to land. I mean, yeah. But then how do you fill up the tank again and all that stuff?
Yeah, field. You have to go get some farmer to get you some AV fuel to put in it. So.
There you go.
Yeah. My grandson is a CFI.
Okay.
He got his degree at the University of North Dakota. Now he's a flight instructor. He's working on his hours so he can go to the airlines. I think I think he's got about 800 hours, so he's getting close.
Oh yeah, he's coming in at a good time too for them.
Yeah, he is. Yeah.
Mhm.
Any other questions? Well, again, Carl, thank you very much.
You're welcome.
Thank Ed for approaching and asking to join us this evening. And again, I'll definitely be in contact with you because
Okay.
I think the Inves conversation would be interesting as well because we do a lot of e-com as our club. A lot of our members are members of Aries groups, either here in Boulder County or Weld or Larimer, Broomfield, places like that. So we stay busy with things like that. So I like to learn a little bit more about Inves myself. So I think it'd be a good conversation and a good topic. So
Okay.
I will be in touch, sir.
All righty.
All right.
Hey,
Well,
good
if nobody's got
night,
anything else, thank you very much. I appreciate
Thank
it.
you. Thank you, guys. You're welcome. So off I go.
Thank you very
Have a
much.
great evening. Thank you. And
Okay.
everybody else, thank you very much as well. And we'll see you hopefully at Field Day next month. Hint, hint. Good night, everybody.
All right.